So my name is Jason Beirne. I'm a postdoctoral researcher in Dublin in Professor Braden's group. So I've joined the Transin project in August of last year, so quite a recent addition. My background was in physics, actually, and in chemistry. And when I joined the project, the prototype 12 that had been developed in Dublin had led to a positive pharmacodynamic effect in rats. But subsequent tests showed some variability in results. So I was specifically hired in August of last year to investigate and optimize the nanoparticle preparation method and ensure the batch-to-batch reproducibility. So firstly, what question did I try and ask or try and address? Well, where in the nanoparticle preparation did the size variability originate from? Well, firstly, why is it important? So from a pharmacological background, the dose of peptide, it's directly related to the size of a particle. So if we have encapsulated peptide chains within a particle, having the diameter of the particle can lead to a factor of 8 decrease in the peptide dosage. So quite a significant decrease. Similarly, the release kinetics of smaller particles will be different than larger particles, obviously, because the surface to volume ratio is larger for smaller particles than larger particles because of the R² dependence. So these two properties can thus be directly related back to the physical properties of the nanoparticles, in this case, the size. So we used a dynamic light scattering technique, which I'm sure a lot of you are familiar with, but for those of us who aren't, our instrument generates a distribution here, a particle size distribution, which is gotten from this autocorrelation function data, which is also taken from fitting of the raw data, which is the intensity fluctuation. So how do we get from here to here? Well, if we look at a single burst, one of these spikes here in the data, we can magnify this, and the autocorrelation analysis, which is shown here on the right-hand side, really looks at the self-similarity of this signal with itself at t equals 0, and then at a time lag later. So if we look at the first time point, we can see that the two signals here, or the signal with itself, is highly correlated, which leads to a positive value here. But then as we move along in the lag time, the signal here becomes less and less correlated, which leads to this point here. And fitting of these points, this data, leads to our particle distribution data here in the end. So are there other techniques that are available? So we briefly looked into this. I've shown some of them here. I'm not going to go into them in great detail, but the last three techniques we could disregard based on size, the size range that we were operating in. So we can look at these other techniques. There are advantages and disadvantages to all of the techniques. Sort of predominantly, my comments regarding TEM and AFM would revolve around it's not particularly suited for peptides. So if we have peptides that are encapsulated, say, within polymer particles, when we're drying down this material, it may be completely changing its morphology when it goes from the wet environment, the wet regime, to the dry regime. So it's not really ideal for some of the peptides that we're looking at. Other techniques such as nanoparticle tracking analysis are good, but they have low sampling. There are other techniques such as this newer TRPS technique, which is good, but it particularly in terms of looking at heterogeneous distributions. But there are some papers which suggest that there is measurement-to-measurement variation due to the device, not due to the batches that go through. So this leaves us with a couple of techniques: DCS, which is a very good technique, but is expensive and high maintenance, or DLS. So DLS we chose because of the wide measurement range ability of the instrument, the good sensitivity, so it can see monomers and dimers, and also it's high throughput, it's rapid, and it gives us non-destructive measurement. So we can measure these particles and then directly put them into another assay or into the animals. So if I go back to the original question, how can we use DLS to look at the variability? And so initially, instead of looking at the reagents or the concentration of recipe or material going in there, I looked at the process. So I'm just showing a video here, hopefully it'll play, of the mixing. So I'm adding in a particular reagent into 4 Eppendorf tubes here that have oversized magnetic fleas in there that are basically oscillating and jumping up and down, giving us different mixing regimes. So hopefully you can see that when I'm adding in the reagent here, it's inducing formation of nanoparticles. But nanoparticles form sort of in this first layer here. And the opacity of this layer is much different because mixing isn't very effective at this point in the tube. Similarly, if you look at this second tube and the 4th tube, mixing actually only happens within this 3/4 length of the tube. It doesn't happen in the top part. So your effective concentrations are different between the tubes. So I'm showing this basically to highlight that mixing is very important, and it can lead to a distribution of sizes in your DLS data at the end, which is what we saw when we prepared our materials in this way. Not only can the mixing affect the size, it can also affect the morphology. So under some preparation conditions, non-spherical morphologies can happen. So one thing that we were concerned about was fibrillation of insulin, which we hadn't seen much mentioned in the project about this, but we actually directly saw fibrillation in some of our early processes, and we traced it back to a mechanical agitation step, where if you're either vortexing or sonicating your material, you can really encourage other pathways, other formation pathways, instead of spherical morphologies. And as you can see in these images, there are no particles present. It's completely fibrils. So there are some interesting papers detailing some of the factors that lead to fibrillation. And particularly, there's one just released, actually, showing that sonication can speed up fibrillation by a factor of 430. So in terms of my conclusions and my learnings from Transient, for biologics, control over the final size and morphology isn't a trivial matter, particularly when working with peptides. We were interested in focusing not only on the ingredients, but really on the process, so looking at mixing, which I think is very important. It's been important for me as well to work in an interdisciplinary collaboration because my own background is in physics and chemistry. I'm not a pharmacologist, so we have worked quite closely in trying to optimize the particle formulations that we've made. So, as I've said previously, the lack of control can be related to either the mixing regime, which is process related, or due to the reagents themselves, conformation, stability, solubility, etc. So finally, the final point that I'd like to get across is that the current techniques that we're using, DLS, circular dichroism, HPLC, and TM, are very important core methods, but I think we can expand on this. So coarse-grained molecular dynamics are a really important tool that a Nobel Prize in Chemistry was awarded back in 2013 for this. The ability to predict systems and what they will do in different colloidal environments, and different solution environments. And also multidimensional NMR for structure determination has been used to look at larger peptidic assemblies, and particularly fibrils. So I think there's an opportunity here to use these techniques. And so the final slide, the scientific output, well, the data that is generated has gone towards a patent. So we haven't released any of the papers until we have the patent filed. We were asked to say what our next career steps would be. Well, I would like to continue working on peptide nanoformulations, but I'm sure everybody says this, current academic opportunities are limited because you need papers. So I'm open to leaving academia to biologics role, but I would like to return to academia in the future to explore this further. Thank you.
Okay, we have time for a couple of questions. So Jason, maybe I can ask you about what's the different approaches of the physical chemist to the nano versus what the pharmaceutical people are doing.
Yeah, so I think one of the important things for me looking at it is from a colloidal perspective. So really focusing in on the size of the particles, and then once you have a stable size formulation, you can really work on your encapsulation efficiency, your release kinetics. But we spent a lot of time really focusing particularly on the size and on seeing stability in our zeta potential measurements, stability in terms of our size. And I think in a lot of the papers that I've seen, people usually quote a single number, the size as being a single number, whereas I've often focused really on showing the distribution of the size. because I think it's very important that you really show that this particle isn't specifically this size, it's within a range where the mean is that size. So that would probably be my perspective on it.
Very good. There's one other question. Trina?
Hi Jason, thank you for that. You mentioned the multidimensional NMR. Could you tell us what kind of extra information we can get from that technique, and do you need very specific instrumentation, or is just the routine NMR enough?
Yeah, so I'll be quite honest, I'm not terribly familiar with the technique, but I know that the technique has been used recently looking at fibrillation of short peptide sequences and longer peptide sequences. And what they've shown is that the multidimensional angle comes from, you're looking at larger assemblies, larger systems. So really you're trying to draw a map of, when you change particular, solubility conditions or reagent concentrations, are you moving the formation towards a different part within your NMR spectrum? So it's really to give you sort of the local information on what the peptide sequence is doing at the nanoparticle level. And I think it could be very useful, for this type of work, but I haven't seen any papers on that. I've only seen it on the fibrillation issue, which is a similar issue to the nanoparticle formation.
Great. Okay, we're going to move on. So thanks, Jason.